In this video, we're going to use the fundamental theorem of Calculus 2 to prove the fundamental theorem of Calculus 1. Okay, so let's start out by defining this area. Let's start out by calling this area here capital G of x. Let's just give it a name, capital G of x. Now, one way of writing this this area here would be to write as an integral from a to x of the function, okay, and then dt. So from here, remember this is just us defining this area to be g of x. There's nothing to think about. It's just us assigning a name to this area here, which is this, and this is the way we would write the area. Okay, so from here, we can then use the second theorem, the second fundamental theorem of calculus to take us to here, because the second fundamental theorem of calculus says that if you differentiate the area, it equals the function itself evaluated at x. Okay, so it will then take us to here. So from here, there's nothing to think about here. It's just us assigning a name g of x to this area here. Then from here, using the second fundamental theorem of calculus, that will then take us to this. And then from here, remember that capital F, and then small f. So when you differentiate this, this is just a notation. It's just a way we would write functions. Well, the thing is, when you differentiate this, it gives you small f. So rather than using small f, we would use capital F, but prime of it. Okay, so when you differentiate capital F, it gives you small f. So rather than using small f, we would use capital F prime of capital F of x. Okay, so that will then take us to this. Let me just re-explain this bit. Hang on. So here we've got one scenario here. This here is another scenario. The two are separated. So well, don't forget, we could say that when you differentiate capital F of x, it gives you small f of x. So sometimes we could use this, sometimes we could use this. The two are exactly the same. So capital F means the two are interchangeable. When you differentiate this, it gives you small f. Okay, well, just remember, this is one scenario, this is another scenario. We define this area to be this. So the second fundamental theorem of calculus says that when you differentiate the area, it gives you the function itself evaluated from a to x. Okay, but then rather than using small f, we would use capital F, but prime. So we would put it into here. So that will then give us capital G prime of x equals, rather than using small f, we would just use the differential of the capital F. Okay, so that will then take us to here. Now when hang on, when you've got when you're at this stage here, there's a theorem on uniqueness of antiderivatives, saying that if the two derivatives are exactly the same, then the two antiderivatives are exactly the same but only differ by a constant. Okay, so when you have, there's a uniqueness uniqueness of antiderivatives, saying that if one derivative is exactly this, if one derivative is exactly the same as the other is the same as the other derivative, then the two antiderivatives are exactly the same, but only differ by a constant. So, for example, if you have a derivative being exactly the same as the other derivative, so for example, let's look at this graph here, y equals 3. If the antiderivative here, if the derivative here is 3, and this is also the exact same derivative, then the two antiderivatives are the same but only differ by a constant. So let's say you've got the derivative being 3, then the antiderivative could be this, or it could be 3x plus 5. The point is that they're all exactly the same, but only differ by a constant. Okay, so when you get to this stage here, then you can well, when you get to this stage here, you can integrate equally. Okay, integrate equally. That will then give you capital G plus C equals capital F of X plus C. Okay, and then so these two constants are, well, you can take away C from both sides, C1 from both sides. So that would then give you this, C2 minus C1, and then this would be GX. And then constant that you don't care about, you can merge them together to give you a new constant, C3. But we don't really care about this. Let's just call it blah blah blah. From here you can jump to here. Okay. So when you get to this stage here, what you've got here is, when you get to this stage here, what you've got is that if you want to know the area, remember we defined capital G of X to be this area. If you want to know the area, then all you have to do is find the antiderivative. It would be you evaluating the antiderivative plus some magical number. So what you've got here is the ability to work out the area here by evaluating capital F and then plus some magical number. We will elaborate more on this in the next video. Okay.